Imaginary numbers ended up with an unfortunate name. Imaginary, generally, most people think doesn't exist. Imaginary numbers really do exist, but they're an answer to a question that we can't answer. You'll see what I mean in a second. We know when we were dealing with roots and radicals, something like the square root of 25, the question is, what times itself gives me 25? And generally, we would take what we say the principal root, and we say the answer to this is 5. But a question that we couldn't answer when we first ended up with these roots and radicals was what is something like the square root of -4, right? It says what times itself gives us a -4. Well, you can see that this can't have an answer, or at least the way we think about an answer, because whatever goes in these parentheses has to be the same thing. If the thing that I pick is a positive number, a positive times a positive is not a negative. Or if the thing that I pick as an answer, if it is negative, a negative times a negative is a positive. So you see, nothing I can pick will work. Well, what this boils down to is this. Any negative number can always be written as -1 times that number. And we know by our properties of roots and radicals, we can break that up. So you see, I've kind of isolated the problem. It's the square root of -1. I know what the square root of 4 is. It's 2, but then you end up with this weird radical here. This does not have an answer. Well, mathematicians, when they were first running into this, said, you know what, that doesn't have an answer, and most of them stopped. And then a mathematician came around by the name of Leonard Euler and decided, hey, what happens if we keep working problems? And he found out that the problems actually still made sense if we kept going after this stage, even though we don't know the answer to this. But mathematicians are pretty lazy people, and they like to use shorthand notation for a lot of things. So instead of writing the square root of -1 everywhere, Euler decided he was just going to replace that with the letter I. Now here's where a little misunderstanding comes into place. The square root of -1 does not equal I, right? The square root of 4 is 2. That's an answer to the question. This isn't an answer to the question. The square root of -1, the answer is not I. It's just a shorthand notation, so we don't have to write that. So we're just replacing this. All right, so now that we have this new I thing, we can try to simplify a few expressions. So what if I said the square root of -8? Well, anytime you see the square root, a negative under a square root, you know you're going to end up with an imaginary number. So one way to deal with this is go ahead and pull out the negative as an I and then simplify what's left over. Now, most of the time when we write these imaginaries, these i's, we treat them like x's, like if we wrote like 5x. We generally like to write the variable to the right. So if we had an I, we would generally write it as 5i, just like the variable to the right again. However, when we have roots and radicals, we generally write the stuff out front. So I'm actually going to pull out that negative as an I. So once that negative comes out as an I, now you can just go about simplifying a radical like you normally would. Now there is a perfect square in 8. Remember, 8 is 2 times 4. So I don't know what the square root of 2 is, so that has to stay underneath. The square root of 4 is a 2, so that can come out front just like before. So we would say the square root of -8 is 2i square roots of 2. Now you may see in textbooks, because, well, they can print and it gets really nice, you may see it written like this, 2 square roots of 2i. Again, because we wrote it on the right. Now the reason we generally don't want to do this by hand is because, well, we're a little messier by hand, and that radical can get all the way over that I sometimes, and that's not the right answer. So be careful. That's why we generally write it out in front, so we don't have that problem. But either one of those are technically correct. All right, now don't get confused though. We don't have the same problem with cubed roots. It's really only the even roots that you're going to end up with some type of imaginary part to your answer. But for a cubed root, remember this says what times itself 3 times gives us a -27. Well, the answer to this is just -3. There's no i's here because -3 times -3 is 9 times -3 is -27. So if you have negatives under odd roots, you don't get any imaginary stuff. You only get it when you have, well, for us, it's going to be under square roots, we get this I thing. Now this I has some pretty interesting properties. So I'm gonna go here, I'm gonna say, if you take this I raised to any power can be simplified into one of the following. 1i, -1, -I. So if you take this I thing, this imaginary unit here, and you raise it to any power, you can actually simplify it to one of these four numbers, which is pretty interesting. So let's see how this works. Let's start out with just making ourselves a table of I to powers. Now, according to our rules of exponents, here I have I to the 0. Anything to the 0 power is 1. I to the first, well, anything to the first power is itself. I squared. Let's see what I squared is. Now remember, I is really the square root of -1. If we square that, when you square the square root, it goes away, so we get -1. Now there's our first really interesting result. Remember, I, the square root of -1, doesn't exist. It's something we can't answer. However, if we square it, we get a number that we do know. We get -1. All right, so for the rest of this table, all I'm gonna do is figure out my answer by doing powers of I. See, like here, I know I times I squared would give me I cubed, which means this side has to be true. So if I did I times I squared is I cubed, it means I times -1 has to be -I. Let's keep going and try a few more here. Let's do I to the 4th. An easy way to get I to the 4th, think about it, would be like I squared times I squared, right? That would give us I to the 4th. So -1 times -1 is 1. I to the 5th. An easy way to see I to the 5th may be like I squared times I cubed, right? Because 2, 3 gives us a 5. So that'd be -1 times -I is positive I. I to the 6th here, I don't know, let's do I squared and I to the 4th. That'll give me 6, right? So I squared times I to the 4th, that's -1 times +1 is -1. Now, if you're noticing something here, we have a pattern starting, right? It goes 1i, -1, -I. 1i, -1. Guess what the next one's probably going to be? Let's do one more here. Let's see, to the 7th, how about the 3rd and the 4th power? That would get us to the 7th, so that would be -I times 1 is, well, -I. There you go. So nice and easy to do, and you see we get this pattern repeating. So believe it or not, all we need are those four right there. Now you do need to memorize these, but there's really only one that you got to air quote memorize, right? Because the first one, we know anything to the 0 power is 1. We know anything to the first power is itself. Now this is the one you need to memorize, and this is the one that you're going to use the most anyway, so you're going to memorize it whether you like it or not. I squared gives us -1. And then to get I cubed, all you gotta do is I times I squared, so I times -1 is -I. All right, so how can we use this knowledge here to help us, figure out something like this? If I said, simplify, what if I said I raised to the 245th power? Well, you could keep going on this table till you got to 245 and figure out what it is, but there's an easy way to do it. Notice that this pattern repeats itself every 4 powers. So all we got to do is figure out how many times 4 goes in here and then look at the remainder. Because when you divide by 4, the remainder has to either be 0, 1, 2, or 3, which means that'll be how many times we go past this pattern. So here's what you do. Divide the power, that's a P. Divide the power by 4. Raise I to the remainder and simplify. Okay, so here's what I mean. Let's start. So we do need to do some long division. So let's see. 4 into 245. 4 won't go into 2, 4 goes into 24, what is that, 6 times, that gives us 24. 0, bring down to 5, 4 goes into 5 once, we subtract, and we get a remainder of 1. Now the remainder is what we actually want. Now the 61 here, that was the result from the division. We actually don't need this, but what this tells us is this pattern here will repeat itself 61 times, and then we'll end up with one extra step basically. So I to the 245th power is the same thing as I to the first. That's our remainder. And since the remainder has to be one of these on this list, we know how that simplifies, and of course I to the first is just I. Okay, so it's very, very simple to simplify I raised to any power. Divide by 4, raise I to whatever the remainder is, which means it has to be on this list, simplify that, and you're done. So very, very helpful. So now that we know that I to any power can be simplified, we should always, anytime we see I to any other power other than just 1 like this, you should simplify it. Okay, let's put a few ideas together, and we'll finish up this imaginary number stuff. In the past, we have what we called our real numbers. Those were all the numbers on a number line. So like 5, 2/3, pi, -16, right? Those are all the numbers. Think about every number on the number line was a real number. Well, now we got a brand new type of number that's not on that number line. These are our imaginary numbers. Now, the way our imaginary numbers look are almost exactly like our real numbers, except for they have that I with it. So it'd be like 3i, 5/4 I, 0.07i, -16i. I already used it. All right, so you see, it's the imaginary numbers look exactly like our real numbers, except for they have the I with it. Well, we now have this set of numbers that we've used in the past, and we got a brand new set of numbers here. Well, if we take these two sets of numbers and we combine them, we get the largest set of numbers we're ever going to deal with, and these are called the complex numbers. And the way we join them is we just take a real number and we add the imaginary number. So it's always going to be the real number plus the imaginary number. So generally the way that we would write it would be some real number plus BI. Now remember, A and B here are just the numbers in front, right? A's are just the real numbers. B's are the numbers in front of the I's. This is the form that we're generally going to leave our answer when we're dealing with complex numbers. The real part plus or minus, excuse me, the imaginary part. So a couple quick examples of complex numbers would be like 2 plus 3i. Now, one of the first misunderstandings that we have with complex numbers is, a lot of times I'll ask the students, how many numbers are here? And they would say 2, which is a reasonable answer because we have a real number and an imaginary number. But when we put them together, we create one number, one complex number. So this here, this is one number. Now that one number has two parts to it. Now, for those of you who think that this is really odd to think about it like this, we've actually dealt with something like this in the past. When we're plotting points, and we have a point out here like 2, 3, the 2, 3 represents one point, but it has two pieces of information. Same idea up here, right? This represents one number, but it has two pieces to it. It has a real piece and an imaginary piece. So we have dealt with something like this in the past that has multiple pieces, but we treat it as one item. So let's take a look at just maybe a few other examples of some complex numbers, kind of like 4 minus 6i, 2/3 minus pi. So anytime you have a real number joined together with addition or subtraction with a, excuse me, an imaginary number, it's considered a complex number. Now, technically though, since all these are under the umbrella of complex numbers, all the real numbers are technically complex numbers. Like the number 5 is also a complex number. The way that we could write it as a complex number, now we don't normally do this, but we could we could write that plus 0i, right? Because 0 is just a real number, so that would also work. A completely imaginary number is also, let's do 3i, right? That's a completely imaginary number, but it's also a complex number because the real part, just like here, is 0. So, completely real numbers and completely imaginary numbers are actually complex numbers as well. All right, so we have these new type of numbers out there, so we need to learn how to do some arithmetic with them. So we'll pick that up in a future lecture.